Hi everybody, welcome back to Trigonometry. Today we are in section 1.3 and we're going to be talking about the trigonometric functions. So I'm going to give you the definitions of the trigonometric functions and then I'm going to show you how to find the function values for the quadrantal angles. So here we go. So let's start with the Pythagorean Theorem. You remember the Pythagorean Theorem from middle school. It says if you have a right triangle where the legs are labeled A and B and the hypotenuse is labeled C, then A squared plus B squared equals C squared. In other words, the sum of the squares of the legs is equal to the square of the hypotenuse. Keep in mind that the Pythagorean theorem is only good for right triangles. It does not work on any other kind of triangle. So before you use the Pythagorean theorem, always look at your triangle and make sure that you see the square here in the corner that guarantees you that this triangle is a right triangle, or you should have some information in the problem that tells you that the triangle is a right triangle. Now the way that the triangle is labeled is important. I mentioned earlier that the legs are labeled A and B, and the hypotenuse always needs to be labeled C. The hypotenuse is special because it's guaranteed to be the longest side in the triangle, and the reason it's the longest side is because it's across from the largest angle. In a right triangle, the largest angle is going to be the right angle. The hypotenuse is across from the right angle, and it's always labeled C. The two other sides, A and B, as I said, are called legs. Those two are interchangeable. In other words, it does not matter which is which, but the hypotenuse must be labeled C. So if you're looking for the hypotenuse of a right triangle, what you're going to do is add the squares of the other two sides and then take the square root. But if you're looking for a leg, if you're looking for A or B, then the Pythagorean theorem has to be solved for that variable. Notice that if I want to solve for A squared, what I would do is subtract B squared from both sides, and that would give me A squared equals C squared minus B squared. Or if I wanted to solve for B squared, what I would do is subtract A squared from both sides, and that would give us B squared equals C squared minus A squared. Notice that regardless of whether you're looking for A or B, you end up subtracting the squares. So to find the leg of a right triangle, subtract the squares and take the square root. So again, if you're looking for the hypotenuse, you add the squares, but if you're looking for a leg, you subtract the squares. And you'll always subtract larger minus smaller. So you'll always start with the square of the hypotenuse and then subtract the square of the other known side. And then remember, that gives you the square of the side that you're looking for. So the last thing you'll do is take the square root. Usually in trigonometry, we leave the answers in simplified exact form. And what that means is we leave the answer in simplified radical form and we don't go to decimal form unless we're doing a word problem or something where that's called for. But most of the time, we leave our answers in exact form. So let's look at an example here. So here we're looking for the length of side C. So C, of course, is the hypotenuse. That means we will be adding squares. So first, let's get the Pythagorean theorem, and then let's plug in our two known sides. So as I mentioned before, it does not matter which of these you call A and which you call B. So I'm just going to write 12 squared plus 4 squared equals C squared. Now 12 squared is 144. And 4 squared is 16. And the sum of 144 and 16 is 160. So we have 160 equals C squared. Now if we take the square root, so we'll have C, then we have the square root of 160 equals C. If you're coming straight from college algebra, you might be asking, well, why don't we have to put the plus minus sign here? Because in algebra, you would put a plus or minus when you take the square root of both sides. But here, in trigonometry, this represents a length, and a negative length does not make sense. So we pretty much just ignore the negative here. But I do need to reduce this radical. And so remember how we reduce radicals. We break this down into the product of a perfect square times whatever else. Notice that 160 is 16 times 10, and the square root of 16 is 4. So the 4 will come outside the radical, and 10 is 2 times 5, so that cannot be reduced further, and this would be our final answer. The length of the hypotenuse is 4 times the square root of 10. Now, if you're doing a problem mentally, I want you to be able to just say 12 squared plus 4 squared, maybe use your calculator to get 160, and then reduce the radical. If you're showing your work on a quiz or an exam, you need to be complete in how you do this. You may not have to show every step that I showed on the last slide, but you do need to show what numbers you plugged in, and then you get your total, and then you show how you simplified your radical, because that is still important. So go ahead and show the work for that. But you just know that because you're looking for the hypotenuse, you're going to be adding the squares of the two sides. Now let's do an example where we are looking for the length of an unknown leg. So in this example, we're looking for the length of side A, and that tells me that we're going to be subtracting the squares here. So I'm going to go ahead and write down our formula, but now we're going to plug in. So of course 15 is side C, that's the hypotenuse. So A squared equals 15 squared minus 6 squared. 15 squared is 225 and 6 squared is 36. Then 225 minus 36 is 189. So now I have A squared equals 189. So when I do the square root of both sides, A equals the square root of 189. So I need to ask myself if this radical can be reduced. And the answer here is yes, because 9 goes into this number. And you might be saying, well, how do you know 9 will go into that number? Well, the rule for divisibility by 9 is that if you add the digits and the sum of the digits can be divided by 9, then the whole number can be divided by 9. So 1 plus 8 is 9. 9 plus 9 is 18. And since 9 goes into 18, I know 9 will also go into this larger number. So now if you don't know how many times 9 goes into this number, you can use your calculator to divide and find out. But what I know is that 189 is 9 times 21. And so then the square root of 9 is 3. The 3 comes outside the radical. And 21 is 3 times 7. And neither of those is a perfect square, so that stays under the radical. Okay, now that we've got a good handle on the Pythagorean theorem, we're going to introduce the trig functions. So the first function is the sine function, and sine here is spelled S-I-N-E. Now whenever you use this in a mathematical expression or an equation, it will be abbreviated, and it's always abbreviated S-I-N. And when you use it in an expression, you must put the angle that you're doing the sine of. To use the function without telling what you're doing the function of does not make any sense. So when I write this in an expression, I have to write sine of theta. Now theta is just the most commonly used symbol for an unknown angle. But it could be sine of x, it could be sine of something else. The most common is sine of theta. The next function is cosine, and cosine is abbreviated COS. So this says sine of theta, this says cosine of theta. The next function is tangent. Tangent is abbreviated TAN, so this says tangent of theta. The next function is cosecant, and cosecant is abbreviated CSC. So this says cosecant of theta. Then we have secant of theta, SEC, secant of theta. And then cotangent is abbreviated COT. Notice that every function has a cofunction. I have sine and cosine. I have secant and cosecant. And I have tangent and cotangent. And you might be saying, well, since we have 3 pairs of functions and cofunctions, why are they written in this strange order? Why did I not group each function with its co-function? And there's a reason for that, but I'll tell that reason to you later. For right now, the most important thing I want you to remember is that it does not make sense to write a function without stating the angle. So I can write sine of theta, but I should not ever write just sine and not put an angle there. That's very confusing. It's not clear at all. It's the same as in algebra. If you just wrote a radical and left it empty, people would be saying square root of what? So you have to put what you're taking the sine of, just like I would need to put a number here to show what I'm taking the square root of. Okay, so now let's get the definitions of the trig functions. Here I have a diagram for us, and notice that my angle theta is here. This angle theta is in standard position. That means that the vertex is at the origin and the initial side is on the positive x-axis. So on the terminal side, I've got a point P, and that point P has coordinates x, y. That means that if we were to draw an imaginary line from point P straight down to the x-axis, we would have a right triangle. And the horizontal side of that right triangle would be x, and the vertical side of that right triangle would be y, and the hypotenuse would be what we're going to call here r. And the Pythagorean theorem says that x squared plus y squared equals r squared. In other words, to find the length of side r, we would add the squares and take the square root. See, it's just the Pythagorean theorem. Okay, now that we have all three sides known on this triangle, the sine function is the ratio of y over r. So sine of theta is y over r. The cosine of theta is going to be x over r. And the tangent of theta is going to be y over x. And you might be saying, well, why? Why does sine have to be y over r? And the answer is, that's just the name of the function. The fraction that you get when you do y divided by r is always called sine. The fraction that you get when you do x divided by r is called cosine. That's just their name. So to say, well, why do they have to be that way is like saying to somebody, why is your name Jim? It just is. So these are the definitions of the trig functions. And then these other three functions, it turns out, are just reciprocals of the first three. So the cosecant function is the reciprocal of the sine function. So sine is y over r. That means cosecant is r over y. The cosine of theta was x over r. Secant is the reciprocal of cosine. So the secant of theta is going to be r over x. And tangent of theta was y over x. That means cotangent of theta is going to be x over y. So now you can probably see why I kept them in this order. Sine, cosine, and tangent have their three definitions that are taken right from the triangle. These other three functions are reciprocals of the first three. So sine and cosecant are reciprocals of each other. Notice sine is y over r, cosecant is r over y. Cosine and secant are reciprocals of each other. Tangent and cotangent are reciprocals of each other. Notice that the functions and their cofunctions are not reciprocals. There is a relationship there, but it's not a reciprocal relationship. For reciprocals, we have matched up sine and cosecant, cosine and secant, and tangent and cotangent. Okay, now here is example 1, and let's read it together. So it says the terminal side of angle theta in standard position passes through the point 8, 15. Find the values of the 6 trigonometric functions of angle theta. So first we need to draw angle theta. So I've got us a coordinate system here. The point 8, 15 would be in quadrant 1. So it might be up here somewhere. I'll just put it here. So that's the point that the terminal side needs to go through. So now let's draw the terminal side of our angle. And so this makes angle theta. Remember, an angle in standard position always has its vertex at the origin and always has its initial side on the positive x-axis. So this is the angle theta. And now if we draw that little imaginary vertical line, we have a closed-in triangle, and because this is vertical, this would be a right triangle. And now we can find the lengths of the three sides. Since the point was 8, 15, we know the horizontal side has length 8 and the vertical side has length 15. And we can use the Pythagorean theorem to find the length of the hypotenuse, which is r. So we'll just say r squared equals 15 squared plus 8 squared. Now 15 squared is 225 and 8 squared is 64. When you add those together, r squared is equal to 289, and that means r is equal to the square root of 289. Now you might not know this one off the top of your head, but if you just hit the square root button on your calculator, if you do the square root of 289, you find out that that's 17. So now we know that the hypotenuse is 17. And to find the 6 trig functions for angle theta, we just use the definitions that we saw on the last slide. So the sine of theta is equal to y over r, which for this angle theta is going to be 15 over 17. The cosine of theta is x over r, which for this theta is 8 over 17. And the tangent of theta is y over x, which for this theta is 15 over 8. And then the other three functions, remember, are the reciprocal functions. So the reciprocal function for sine is cosecant. That means cosecant of theta is 17 over 15. The reciprocal function for cosine is secant. That means the secant of theta is 17 over 8. And the reciprocal function for tangent is cotangent, and that means the cotangent of theta is 8 over 15. And again, just a reminder, make sure when you write these that you don't just write sine equals 15 over 17. It needs to be sine of theta equals 15 over 17, cosine of theta equals 8 over 17, etc. Here is a similar example. This one says the terminal side of angle theta in standard position passes through the point -3, -4. Find the values of the 6 trig functions of angle theta. So -3, -4 means that point is to the left and down from the origin. So I would say that -3, -4 might be about right there. That means the terminal side of theta goes through that point. So angle theta, being in standard position, goes from here to here. So that's angle theta right there. Now to find the 6 trig functions for this angle, we need to close in our triangle. So we'll draw an imaginary vertical line that goes to the axis. And then we know that the horizontal side of this triangle would be 3 units long. The vertical side would be 4 units long. I did not use the negatives because we're talking about lengths of a side of a triangle here. So the coordinates of the point, the x and the y, are negative, but the lengths that we're working with here when we use our Pythagorean theorem, those are not negative. So now I need to find r, so I'll say r squared equals 3 squared plus 4 squared. That means r squared equals 25 because 3 squared is 9, 4 squared is 16. Add them together, you get 25. And that means r is 5. So the hypotenuse is 5. And now we will use our 6 trig function definitions. Remember, sine of theta is y over r. Y is negative. So when we do y over r, we're going to have -4 over 5. It's important to keep in mind that r is always positive. R cannot be negative. This point has negative coordinates, but this length here is positive. R is a length, it must always be positive. So the sine of theta is -4 over 5. The cosine of theta is x over r, so x was -3. So cosine is going to be -3 over 5. And the tangent of theta is y over x, so that's going to be -4 over -3. And when you simplify that, negative divided by negative is positive. So the tangent of theta actually comes out positive. So we have 4 over 3. Now the other three functions are reciprocals of these three. So the reciprocal of sine is cosecant. That means that the cosecant of theta is negative 5 over 4. Notice I flipped the fraction upside down. I did not move the negative. Always leave your negative either in the top of the fraction or out in front of the fraction. Never put your negative in the denominator. So the cosecant of theta is negative 5 over 4. The secant of theta is negative 5 over 3. And the cotangent of theta is 3 over 4. So now we're going to take a little exercise from the homework. It says, suppose that the point x, y is in the indicated quadrant. Decide whether the given ratio is positive or negative. Remember that r is always positive. Drawing a sketch may help. So we are going to start with a little sketch. Here I've got us a coordinate system. And remember that the quadrants are labeled quadrant 1, 2, 3, 4, starting in the upper right and going counterclockwise. Now here in quadrant 1, all the x values are positive and all the y values are positive. So let's just write that. X is greater than 0 and y is greater than 0. That's how we write positive. So x is positive, y is positive. In quadrant 2, x is negative, so x is less than 0, but y is still positive. In quadrant 3, x is negative and y is negative. And in quadrant 4, x is positive while y is negative. So now, if you are looking at an angle in quadrant 2, and you're looking at the ratio x over r, which we know now is cosine, then in quadrant 2, your x would be negative, and r is always positive. So what you're looking at here is a negative divided by a positive, which is always a negative value. So in quadrant 2, x over r is always going to be negative. The next one asks us about quadrant 4. So it says for quadrant 4, will y over r be positive or negative? So we look at quadrant 4, and in quadrant 4, all the y's are negative, and of course r is positive. So y over r would be a negative divided by a positive, which again is negative. The next one says in quadrant 2, look at the ratio y over r. So in quadrant 2 again, this time we're thinking about y over r. So y would be positive, r of course is positive, and positive divided by positive is positive. On the next one, in quadrant 3, we want to look at the ratio of y over x, which we know is tangent. So quadrant 3, y over x would be a negative number over a negative number. Negative divided by negative now is positive. So in quadrant 3, all your tangent values are going to be positive. Now we're going to shift gears a little bit. We've been talking about function values for angles that are in a quadrant. Now we're going to talk about function values for quadrantal angles. So a quadrantal angle is an angle whose terminal side falls on an axis. These angles are not considered to be in a quadrant. Instead, they are what's called quadrantal angles. So here in example 4, it says find the values of the 6 trig functions for an angle of 90 degrees. And so you can see they've drawn us here an angle in standard position that's 90 degrees. And you can see that the terminal side goes through the point 0, 1. So we have x and we have y. To find the 6 trig functions, of course, we need r. Now we normally would use the Pythagorean theorem to find r, but you don't really have a triangle here. So remember that r is the distance from the origin to the point. And because the terminal side is on an axis, we really don't even need the Pythagorean theorem here. We can just count. The distance from the origin to this point is just 1 unit. So you can just count it. So we're just going to say that r equals 1. And now the sine of 90 degrees would be y over r, which is 1 over 1, and that, of course, is 1. Then cosine of 90 degrees would be x over r, so that's 0 over 1, which is 0. Tangent of 90 would be y over x, which is 1 over 0, and that is undefined. Remember, anytime you have 0 in the denominator, that's an undefined value. And then cosecant of 90 degrees is the reciprocal of sine. The reciprocal of 1 is 1. Secant of 90 degrees is the reciprocal of cosine. So instead of looking at this simplified value, look at your fraction here, because we know secant is the reciprocal. So turn this fraction upside down, and you'll have 1 over 0. And of course, 0 in the denominator means this value is undefined. And then for cotangent of 90 degrees, that would be the reciprocal of tangent. So that's 0 over 1, so that's 0. Now, one thing you can take away from here is that if you have 0 on the top, that value is 0. If you have 0 in the bottom, that value is undefined. Also, we can think of it this way. The reciprocal of a 0 value is an undefined value, and the reciprocal of an undefined value is a 0 value. So you really, if you know that, you don't ever have to go back to the fraction anymore. Okay, for part B, we'll do pretty much the same thing. It says find the values of the 6 trig functions for an angle theta in standard position with a terminal side through -3, 0. And they've drawn that for us here. Here is theta. And of course the terminal side goes through -3, 0. Notice that this is a 180 degree angle. So it does go through the point -3, 0, but it also goes through the point -1, 0. So you can use any point on the terminal side that's easy for you. We're going to go ahead with the -3 here. So of course we need r. And since our point is on an axis, we'll just count 1, 2, 3. So r is 3. And now we'll use our 6 trig definitions. So the sine of this 180 degree angle is y over r, which is 0 over 3, which is 0 of course. Cosine of 180 is x over r, so that would be -3 over 3, which simplifies to -1. Tangent of 180 degrees would be y over x, so that's 0 over -3, which again is 0. For the other 3 functions, we'll just use reciprocals. The reciprocal of sine is cosecant, so the reciprocal of 0 is going to be undefined. And the reciprocal of cosine is secant, so the secant of 180 degrees is the reciprocal of -1, which is -1. And the reciprocal of tangent is cotangent. So the cotangent of 180 degrees is going to be the reciprocal of 0, which is undefined. Now, we actually would like to have a little more convenient way to find the function values for quadrantal angles. We don't want to have to count r every time. So we use this idea called the unit circle. And the unit circle is just a circle whose center is at the origin and whose radius is 1. And that's why they call it the unit circle, because its radius is 1 unit. Since r is 1, these 4 points on the axes become very easy to identify. This point is 1, 0. This point is 0, 1, then -1, 0, and 0, -1. And since r is known to be 1, that simplifies our definitions. So on the unit circle, the sine of theta, which we know is y over r, becomes y over 1, which simplifies to y. And the cosine of theta is x over r. On the unit circle, that's x over 1, which simplifies to x. So this is why we like the unit circle, because it frees us from having to think about r. Sine of theta is just y, and cosine of theta is just x, as long as your points are taken from points on the unit circle. So let's practice with that idea here. So I've got us a diagram of the unit circle. Remember, the x-coordinate is the cosine of your angle, the y-coordinate is the sine of your angle, and then for tangent we'll just do y over x. So all you have to do is use the angle to locate where your terminal side would be, and then use that point for your x and y. So here we have cosine of 90 degrees. Now, with your angle in standard position, of course, the initial side never moves. It's always along the positive x-axis. So to get a 90-degree angle, the terminal side is going to have to go up through the top of the circle. So the cosine of 90 is the x-coordinate from this point. So the cosine of 90 is 0. For b, we have the sine of 270. So the sine function is the y-coordinate. So we just need to locate the terminal side of a 270-degree angle. So if I'm starting here, I would have 90, 180, 270. 270 degrees terminal side would go through the bottom of the circle. So the sine of a 270-degree angle is -1. For the tangent of 180, we locate the terminal side of 180 degrees, which is going to have to go through the left side of the circle, and then tangent is y over x, which is 0 over -1, which reduces to 0. For part D, sine of 0 degrees. So the terminal side of 0 degrees would go through the right side of the circle, and the sine is the y-coordinate. So the sine of 0 degrees is 0. Cosine of 270. Again, the terminal side of 270 goes through the bottom of the circle. Cosine is the x-coordinate, so the cosine of 270 is 0. And tangent of 90. We know the terminal side of a 90-degree angle goes through the top of the circle. So tangent is y over x, so that's going to be 1 over 0, which is undefined. Now let's practice a little more, but this time we'll have negative angles. And remember that whenever you have a negative angle, the terminal side goes clockwise around the coordinate system. So here for cosine of -90 degrees, we'll start here at the positive x-axis and we'll rotate clockwise 90 degrees. So the terminal side would go through the bottom of the circle. Cosine of -90 is going to be 0. For part B, we have sine of -270. Now this is negative, so starting from the positive x-axis, we'll rotate 270 degrees clockwise. So 90, 180, 270. And a -270-degree angle would have its terminal side going through the top of the circle. So the sine of -270 is 1. Cosine of -180. So we start here. We go clockwise 180 degrees, and the cosine of -180 is -1. For sine of -180, well, we're still here with our terminal side going through the left side of the circle, so the sine of -180 is going to be 0. The tangent of -90 means that we rotate clockwise 90 degrees, and tangent is y over x, so that would be -1 over 0, which is undefined. And for cosine of -270, again, the terminal side would go through the top of the circle, and cosine is the x-coordinate, so the cosine of -270 is 0. Now, I'm sure you've noticed that we haven't done any examples yet with secant, cosecant, or cotangent, and we are about to do that. So let's just kind of put together what we know about the reciprocal functions with what we know about the unit circle. So we know that cosecant is the reciprocal of sine. So if the sine of theta is y, then the cosecant of theta is going to be the reciprocal of that, which is 1 over y. Secant of theta is the reciprocal of cosine of theta. And if cosine of theta is x, that means secant of theta is going to be 1 over x. And cotangent, of course, is the reciprocal of tangent. So if tangent of theta is y over x, then cotangent of theta is going to be x over y. And we already knew that. But you probably had not thought about the definition of cosecant and secant in exactly this way. Now, of course, you've noticed already that sometimes tangent is undefined. Well, all three of these functions can also be undefined at times. So now we're going to think about which functions are going to be undefined under which circumstances. Alright, so what makes a function undefined is if its denominator equals 0. So secant and tangent both have x in the denominator. Therefore, secant and tangent are both undefined if x equals 0. And that's going to be your angles that have a terminal side that is vertical. So, for example, tangent of 90 degrees is undefined, and secant of 90 degrees is undefined. Also, tangent of 270 is undefined, and secant of 270 is undefined. Now, the functions that have y in the denominator are cosecant and cotangent. So, these two functions are undefined if y equals 0, and that's going to be the functions that have a horizontal terminal side. So, for example, 0 degrees and 180 degrees would both have cosecant undefined and cotangent undefined. And then finally, for sine and cosine, as you know, sine of theta equals y and cosine of theta equals x. So these don't have denominators, and therefore these two functions can never be undefined. And if you're talking about angles that are not quadrantal, where you do have like y over r and x over r, well, you know r is the distance from the origin, and therefore r can never be 0, so you still would never have a time when sine or cosine are undefined. So now let's practice again by evaluating these functions. Okay, so we have cotangent of 90 degrees. Well, as you know, the first thing we do is we locate where the terminal side would be. So the terminal side of 90 degrees would be going straight up, so out the top of the circle, and cotangent is x over y, so that would be 0 over 1, which is 0. For part B, cosecant of negative 180 degrees, so for negative 180, we go clockwise 180 degrees, and so the terminal side will be going out the left. Now cosecant is 1 over y, so that's going to be 1 over 0, so the cosecant of negative 180 is undefined. For part C, tangent of 0, well, 0 would have its terminal side going out the right of the circle, so that would be y over x, so that's 0 over 1, which is 0. Secant of negative 270, so for negative 270 we go clockwise 270 degrees, so that terminal side goes out the top of the circle. Secant is 1 over x, so that's 1 over 0, so secant of negative 270 is undefined. For part E, secant of 180, so 180 will make us rotate 180 degrees counterclockwise, and so the terminal side goes out the left side of the circle. Secant is 1 over x, so in this case 1 over negative 1, so the secant of 180 is negative 1. For cosecant of 90 degrees, of course, the terminal side of 90 goes out the top of the circle. Cosecant is 1 over y, so that's 1 over 1, which is 1. For part G, we have cotangent of 270. So starting at the positive x-axis, we rotate 270 degrees counterclockwise, and the terminal side is pointing down through the bottom of the circle. So cotangent is x over y, that would be 0 over negative 1, which is 0. And then for tangent of negative 90, of course, that's in the same position because we go clockwise 90 degrees. So again, the terminal side goes out the bottom. Tangent is y over x, so that would be negative 1 over 0, so that would be undefined. Now let's think about what happens if an angle is not between 0 and 360. Well, it's really easy. All you need to do is add or subtract 360 degrees as many times as you need to find a coterminal angle that you can work with, and then you can go ahead and use the unit circle as before. So if we need to evaluate, say, cosecant of 540, well, that may be too big for me to easily find where the terminal side would fall. So what I can do is go 540 degrees minus 360, and that's 180. So now I know that the terminal side is going to go out the left side of the circle. Cosecant is the reciprocal of the y-coordinate, so that's 1 over 0, so that's undefined in this case. And then next, for cotangent of negative 450, well, this is a negative angle. So what I would do is I would add 360 to that, and I would see that negative 450 is coterminal with negative 90. Well, negative 90 is easy to find because I just go clockwise 90 degrees. So the terminal side is going to go out the bottom of the circle. Cotangent is x over y, so that's going to be 0 for this angle. And then for the sine of 720, if 720 is too large, I can just subtract 360, and of course that leaves 360. And obviously if I subtract 360 again, that angle is going to be coterminal with 0. So the terminal side is going out the right side of the circle, and the sine here is just equal to y, so the sine of 720 is 0. Now here is a table that has all 6 trig functions for each quadrantal angle in the first rotation around the circle. Notice that 0 and 360 are coterminal, so their values are exactly alike. You really only need 4 rows of this table. But I don't want you to memorize this. I cut it out of your book and pasted it here just so you could maybe see how the patterns work. But this is not something that you should memorize. Instead, you should be able to find all the trig function values of any quadrantal angle in the way we have been doing on the last several slides. So don't memorize, but learn how to use the unit circle. Now, I do want to point out that you can use a calculator. If you do want to use a calculator, if you're in a situation where you can, then make sure that the calculator is set in degree mode, not radian mode, because 90, 180, 270, 360, those are all measured in degrees. If you have your calculator in radians, of course, it's going to give you wrong answers. But also be aware of the requirements for your class, because some of you may have a quiz or a test where you're not allowed to use the calculator. So before you depend on the calculator too much, make sure you're aware of whether you're going to be required to do this without a calculator or not.